So the robots are going to go to their locations, and we've got GPS locations outside, but the robot needs to know how to get there. So it needs to know two things: how far it is away from that point, and whether to turn the steering wheels left or right. Yeah, because we input 180 before as a test, but we want to know what the real bearing to these points really is. So if you always imagine that there's a compass on the robot, okay, so the bearing from the robot, so forget the fact that it's north, south, east, west, okay, this is just, forget the north, south, east, west, it's just think of the degrees now, and this will rotate with the robot itself. So if you've got a point, and this is, I put here goal north and goal east, okay, so these are points on a grid. From the robot, what is the bearing from the robot to that point? Now, looking at this protractor, it's around about 120 degrees. And the key is, we want to rotate the robot until the bearing difference is 0. So we're basically always churning until the bearing of the robot matches the bearing of the goal. And that's how you get to the points. Okay? So you just imagine that this is fixed onto the robot and it's moving around with the robot. But we are going to use the compass and the location of the robot and the location of the goal as well. And I will talk you through all this. When we use latitude and longitude, we represent it as northing and easting. You might have heard of latitude and longitude as degrees latitude and degrees longitude. Okay? And I thought this might be the next lecture actually that I talk about. But for now, we're just going to use northing and easting. There is a conversion that happens. So we'll just put the degrees to one side, and we're going to use meters. So there is actually a meters grid reference around England. Okay? Now there is one around Scotland as well. I'm not sort of saying or anything like that, you know. But there is a different grid reference. So there's a grid reference around England, and there's a grid reference around Scotland. There's a grid reference around Norway. There's a grid reference around Sweden, and there's ones around France. They're all slightly different grid references. Okay, they've all got different keys. But around England, and it starts off around Cornwall, down on the bottom left-hand side, the coordinates just off the Sea of Cornwall are 0, 0. So that's Cornwall down there. Now, up here, we're about 53,000 metres away from Cornwall in the north, and so many in the east as well. I can't remember what we are, but it's quite a high number. We're talking about thousands here, about 50,000 odd. Okay, but we're going to start off nice and simple and just say, let's imagine our grid reference and we're working around Cornwall. So we're only working in simple metres away. Okay? Doesn't matter if we're talking thousands or not. So what I'm going to do now is just talk about bearing from a point and introduce a function which will tell you the bearing to the point, but I'll show you how it works. So what we're going to look at is what is the bearing and distance to the points from 3, 3. So that's 3 on this one and 3 this way. Okay, 3, 3. So we always start off with x first, don't we, and then y. The coordinates here are 3, 6, and we know that the bearing is 0. If we take that compass and put it here, it's straight ahead to 0. If we could look at another point, so this would be 6 on the x-axis and 3 on the y-axis, the bearing from a compass here would be 90. We've got a bearing here, so this is 3 on the x-axis and 0 on the y-axis, so that would be 180, and that would be 270. Okay, so that's how bearing works. So your goal, this will be the robot, and this will be our goal point, and we need to calculate the bearing to that point. Now, you've probably all done trigonometry, right? And you've used tan. So inverse tan will give you bearing, okay? So that's one way of calculating it. I've actually written a function that uses the tan function. In computers we use something called atan2. Because tan, you might remember from trigonometry, and all trigonometry really, it works in quadrants, doesn't it? It works between 0 and 90, it's going to be plus and minus, and then between 90 and 180 you've got certain values, then 180 to 270, 270 to back to 0 again. With tan, it only works, I think, between 0 and 180. It doesn't give you the full values. So in computing, we use atan2, because let's say you've got a coordinate of -5, -5. If you divide -5 by -5, it makes a positive number. So what's the difference between -5, -5 and 5, 5? It will think it's the same bearing of 45 degrees when it's not. Okay, it's actually in the quadrant, in a negative quadrant, or because we're using bearing, it will be around about, what, 250 degrees, something like that. Okay, but I've written a little function, and that is in your function reference, which is bearing to point. And this is something I want you to be using in the next task as well, the next hour, is bearing to point takes in your current northing, current easting, goal northing and goal easting. Now, northing is actually on the y-axis, so just think, we'll get away from thinking of x and y for now. So northing is going up and down, and easting is going left to right. Okay? So, for the first bit, you would put in 3, 3, and goal northing and goal easting. Let's have a look at this one, for example. No, let's do one where the northing and easting is different. Now, let's do this one. So the northing for the goal is 3, and the easting is 0. Okay, so in this one you would put 3, 3, and then northing is 3, easting 0, and that will return what the bearing is. How do you show the bearing? Well, you use the liquid crystal display. So you can make a variable called bearing if you want, and then you can print bearing. You should all know how to do that by now. Okay, now the other command I've got is distance to point, and this will tell you the distance in meters. So you can put 3, 3 and 6, 6, for example, and that will return the distance to a point in meters. You all know how to do that, I know anyway, in Pythagoras' theorem, yeah? The square root of x squared minus y squared plus x squared minus y squared of the point 2. That's all that code is actually doing. You could actually do it that way if you wanted, but it's always good to use functions that people have written. It makes life easier.